All right, we got one tiny new thing in this video and then just more practice. So the only difference between indefinite and definite integrals is one has limits of integration. And we can deal with that in one of two ways. What we could have done is just found the antiderivative the old-fashioned way and then just plug in the limits of integration from there. But we can actually save ourselves a little bit of time if we change the limits of integration in terms of u. So here's what I mean by that. We're going to explain that in an example, but that's all you have to do for this. Example 4. Evaluate the following definite integrals. Part A is going to look at the integral from 0 to 1 of x squared times 1 plus 2x cubed to the 5th dx. Again, we can evaluate the antiderivative just like we've been doing this whole section, and then plug in 1, plug in 0, and subtract. But there's an even easier way, well, quicker way of doing it. I keep rolling up my sleeves. I could just... Wait, I don't have my lights on. This is a disaster. How's my green screen supposed to function? All right, we're just going to use a u substitution and also substitute the u for those limits of integration. Perfect. So here's what I mean by this. So again, we're looking at the inside function here and saying, well, if we take the derivative of this inside function, we get something like this on the outside. That's great. And so this looks like prime candidate for u substitution. So we go off to the side and say, well, if u is 1 plus 2x cubed, what is the derivative of u? Well, it's going to just be derivative of 1 is nothing. So we just get 6x squared. And again, you can either add the 6 and get rid of the 6, or you can solve for dx. du is 6x squared dx. So dx is du divided by 6x squared. Both methods are fine. So we can substitute this in. That'll eventually cancel out this guy. And then here's the new thing. If u is 1 plus 2x cubed, well then what happens if x equals 0? How do I want to write this? Let's use blue. If x equals 0, well then, what does u become? If x is 0, u is 1, right? U is going to be 1 plus 2 times 0 cubed. U is just going to be 1. So this updates to a 1. And likewise, the upper limit is if x is equal to 1, what happens to u? Well, plug in 1. If x is equal to 1, u is 3. So when we get our new integral, we're going to have now the integral u is going from 1 to 3. X squared, we haven't subbed that out yet, times u to the 5th times dx, which is du over 6x squared. And the x squareds cancel, and we can write the 1/6 in front if we want. Again, cleaning this up, this is 1/6 times the integral from 1 to 3 of u to the 5th du. So the advantage to this method that I'm doing in the blue here in the corner is that we never have to put things back into x's anymore. We can actually just evaluate because everything is in terms of u, and our final answer is just going to be a number. Whether x's or u's, the final answer will be a number. So we don't have to worry about going back. So that's a shortcut that you can use for definite integrals on u substitutions. Again, if you want to find the antiderivative the old-fashioned way and get everything back in terms of x's, you can, but this usually makes things cleaner. Shorter and cleaner and not too messy, I think, which is a good combination. So we can take the antiderivative with the power rule, add an exponent, divide by that exponent, plus c, but we're doing a definite integral, so it doesn't matter what c we use. We're evaluating it from 1 to 3. And again, you can actually factor out the 6 if you'd like, and write this as 1 over 36 times u to the 6th evaluated from 1 to 3. If you factor it out, it just makes your calculations a little nicer, but you don't have to. So we get 1/36, and we get 3 first. 3 to the 6th minus 1 to the 6th. 3 to the 6th, I'm not doing that in my head. I could, but I don't think it's worth it. And it would take a bit. I would not be able to do it. That's a D. 729. 1 to the 6th, I'll do that one in my head. So we get 728 all over 36. There's two ways of knowing that this is not divisible by 3. We know it's not divisible by 3 because this is only 3's and we subtracted 1. Or you could count up the digits. 7 plus 2 plus 8 is 17. If that sum is divisible by 3, then the whole thing is. That's one of the rules. But we do know it's divisible by 2. We divide the top and the bottom by 2. Actually, the top and the bottom are both divisible by 4. And we'll get a 9 on the bottom. And when we get 728 divided by 4, we get a 182 on the top. Again, is still not divisible by 3, so that's our fully simplified answer. For definite integrals, it's a little harder to check your answer, but you can definitely use technology to do so. Integral from 0 to 1. 1 of x squared times 1 plus 2x cubed to the 5th. dx was 20.2 repeating. And we said the answer was 182 over 9. Beautiful. You'll love to see it. Also, you can see this another way. You can write our new integral, the integral from 1 to 3 of just u to the 5th du with a 1/6 out in front. So this is what our integral looked like with substitution, which again is also the same value. Okay, so a bunch of different ways of checking your answer along the way. If our final answer was wrong, I would have then gone and checked this answer. Because if this answer is right, then we know that it's in the second half of the problem that the error is. But if this answer didn't match up with the correct answer, then we know that our error is in the substitution part. All right, and you know, you guys know me. I always try to do my best to give you good examples of trying to find errors. You know, I purposefully make errors so that I can show you how to find them. I haven't made any bad errors recently. Knock on wood. Don't want to. Yeah. Anyway, let's do part B. Part B is the integral from 0 to 1 of x times e to the 4x squared plus 3 dx. We haven't done a lot of exponential functions since the introductory video. My wrist feels a little weird today. So, but our inside function here will just be what's on the inside of the exponential function. And that'll be our guess, and we'll see if it works. All right, so over here, whoa, we're going to guess that this is our u. And if u is 4x squared plus 3, well, the derivative of u with respect to x is going to be 8x. So our du is 8x dx. Now we could either multiply by 8 and divide by 8, or we could solve for dx. In this case, I'm going to multiply by 8 and divide by 8. Show this other method. I try to usually be consistent, but go the shortcut method. Then this blue line just becomes du. Everything under the blue squiggles is exactly equal to du. And we know that if x is equal to 0, what is u? Well, it'll be 4 times 0 squared plus 3. All right, so our lower limit becomes 3 in terms of u. And if x equals 1, we know u becomes 7. So this becomes 1/8 the integral now from 3 to 7, because x equaling 0 is the same as u equaling 3. X equal to 1 is the same as u equaling 7. The 8x isn't there anymore. That's becoming a du along with the dx. And all we're left with is e to the u. You can check your answer at this point too if you want by substituting everything back. Put this in for du, put this back in for u, and you should get, again, the start. Because I know there's a lot of things that's going between these two steps. So it can be a really good idea to check your work that way. All right, so an antiderivative of e to the u is e to the u. We don't need to write the plus c. It's a definite integral. The plus c's always cancel with definite integrals. And now we just plug in 7 and plug in 3. You can either leave the 1/8 factored or put it inside. E to the 7th minus e to the 3rd, e to the 3rd. And that's what you get as our exact answer. Most of the time on this class, I'll want an exact answer. But you may also find a decimal approximation. Decimal approximations are usually preferable for application problems. But this is basically as simplified as you can go. You could maybe factor out an e to the 3 e cubed, but I don't think that's super useful. And we could check our answer with Desmos or something, but we're not gonna here. I'm confident. Integral from 0 to pi over 2 of cosine squared of theta d theta. Now, let's show problem-solving strategies. There's a special trick on this problem, but I do want one example. I always say that we don't know what u is. I always say, like, sometimes you just have to choose it, but I'm not actually doing that to show you guys what it looks like. So in this one, I'm not going to tell you the trick just yet. I'm going to say, okay, this looks weird, but the only inside function we have is cosine of theta. There's no other inside function to choose. If u is theta, that does nothing, just changes the variable. And I'm nervous because I want the derivative of u somewhere. I want a sine somewhere. Give me a sine. And before we dealt with that, like we could multiply by 6 and divide by 6. But we certainly cannot do this. Do not do this. Why is this a problem? Because you can't just take variables out of an integral. Unless the variables, well, in like Calc 3 and something, certain variables you can do. But certainly not thetas. Anything with theta cannot come out in front. You cannot do this. This is bad. This is going to get you fined. The math government send you a fine in the mail. All right, so let's guess and see. Maybe this is it. Well, then du dx, sorry, du d theta is negative sine of theta. So du is going to be negative sine of theta. D theta, which is not really helpful. So let's try to find d theta. D theta would be du over negative sine of theta. And if we do this, you don't have to write this down because I already told you it's not going to work. So I'll go through this a little quickly. If we do this, we're going to get u is cosine of 0, which is 1, up to cosine of pi over 2, which is 0. Of cosine squared becomes u squared, and d theta becomes du over negative sine of theta. So we had an issue that was very similar to this in the past. And that was this example, where the x didn't substitute out all the way. So we just solved for it. And then if we solve for the x with a u sub formula, we got something really nice. That's going to be really hard to do here. It's actually possible. So I said we're going to do a way that doesn't work. It's actually kind of possible. What we'd have to do, and I won't recommend it, what we'd have to do is then if we solve for theta, right? Because we have to get rid of this. If we solve for theta, we're going to get theta is like arc cosine of u, which is kind of weird. And then we'd have to simplify the sine of arc cosine of u, which you can do that by like setting up those triangles. If you remember trig, and you're going to get a fraction, you're going to have to use the Pythagorean theorem, and it's a good trig problem. And I'm almost positive it's going to give you the right answer. But this is not the intended method of doing this problem. Okay? This is not the intended method. Although I'm surprised and kind of happy and a little excited that it would probably work. Anytime you're dealing with trig, yes, you need to remember your calculus. Yes, there are trig formulas for calculus. But you also have to remember your trig simplification. And when you're solving integrals, if you have a trig integral that doesn't look easy, consider some things that you can do to simplify. Okay, so what are some ways that we can simplify cosine squared? Now, again, you're going to have to get out your trig notes. And there's a couple ways. Pythagorean identity is a very, very, very common choice. Sine squared plus cosine squared of any angle is equal to 1. But here we're going to use the power reduction rule, okay, which is really closely related to the double angle formula. Okay, and so go back into your trig notes. Remember that cosine squared of any angle is 1 plus cosine of double that angle divided by 2. And that's going to make this integral a lot more manageable. So if you're ever running into a wall with a trig integral, try to use some substitutions and rewrite that integrand. All right, and that's going to be the trickiest thing you're going to see in this section is something like that with trig. So again, hopefully you have, a single page somewhere. You can Google like trig identities and get everything on a single page as well that you can use. And that's what we'll do here. So let's do that. We're going to get the integral from 0 to pi over 2. Cosine squared becomes 1 plus cosine of 2 theta over 2 d theta. And now we'll factor out a 1/2 and solve the antiderivative that way, or the definite integral that way. 1/2, same limits of integration, 1 plus cosine of 2 theta, d theta, and now we'll integrate each of these individually because they're added together. If the integrand is two functions added together, you can do them individually. Think polynomials. If they're multiplied together, that's where we have to use some other methods. So when we do this, the first one, we can integrate directly. The second one is a simple u substitution that we've actually dealt with a little bit before. And I'm not actually going to do this full u substitution, but you can. And we're going to get that the antiderivative is just theta. Antiderivative of cosine is sine. We have to compensate for the chain rule with that 1/2 right here. Evaluated from 0 to pi over 2. And again, we can check our answer on this guy. Is the derivative of the bottom thing the top? Well, derivative of sine is cosine. That's good. Leave the inside the same as 2 theta and multiply by the derivative of the inside. Multiplying by that 2 cancels out that 1/2. And we're good for that antiderivative. You can also do that with a u substitution, which I'm not going to do that here since I know this is the u substitution section, but it's a very straightforward u substitution. And by this point in the video, I don't think it's necessary. We're going to get 1/2. We're going to plug in pi over 2. Pi over 2 plus 1/2. Sine of double pi over 2 is sine of pi. Minus if we plug in 0, we're going to get 0 plus 1/2. Sine of double 0 is just 0. And we'll simplify. This becomes pi over 2 plus 1/2. What is the sine of pi? Pi is a quadrantal angle. We can think about the unit circle. Sine is the y-coordinate. So what's the y-coordinate at pi radians? Well, the y-coordinate is 0. And same with 0, sine of 0. That's the y-coordinate is 0. Which is also 0, so that whole second thing is 0. We got a lot of zeros, everyone. We're just left with pi over 4. Right? Because that's zeroed out. That's zeroed out. 1/2 of pi over 2 is pi over 4. And we can check our answer. Integral from 0 to pi over 2 of cosine squared of theta. I'll write it like this. D theta is that pi over 4? Neato. My grandma says neat a lot. I also say neat a lot. There we go. We did it. So there actually are two ways. One of them, and this shows, again, I really wanted to show what happens if you try U substitution, but maybe the wrong U or the wrong simplification step. Those are some things that you can consider, some things that you try, and actually there is a way to make that one work. There's some technicalities in getting it to work, but that's what is going on. But here's the way that you're actually supposed to do this problem. Hope that we had 3 videos on indefinite integrals, only 1 video on definite integrals, but we'll get some more practice in the next video as well. Good luck. Bye-bye.